Welcome to the 7th lecture on my series on vector calculus. Now that we have met all the three main players of our story, the gradient, the divergence and the curl, it is now time to look at some useful identities obeyed by these players. These identities essentially involve application of these operations on products or products of these operations. Now the subtitle that you can see here should remind many of you of high school calculus, where delta and epsilon are quantities, very small positive real quantities, which are involved in the definition of limits and continuity of functions. This delta and this epsilon are not the same as those. These are symbols which have specific meaning and which makes many calculations involving vector calculus and indeed vector algebra much simpler and faster. So in the first lecture, we are going to go back to vector algebra, basically dot and cross products, and there meet these symbols, the Kronecker delta and the Levi-Civita epsilon symbol. As the edit that I carried out right now would tell you, in today's lecture, I'm not going to really talk about calculus. I'm going to talk about vector algebra. That's a simpler field, and that's where we will get to meet our delta and epsilon symbols. In the next lecture, we will come back with the tools that we learn about in this lecture and express our holy trinity, the gradient, the divergence, and the curl, in this language, the new language that we are going to learn today, and use it to prove many important calculus identities. Even if these things, the delta symbol and the epsilon symbol, are new things to you, it is well worth your time and effort to learn about them because they will make your life a lot simpler in the future. In addition to these symbols, we will need to meet a famous convention, the so-called Einstein summation convention. It was introduced by Einstein while describing his general theory of relativity, where the equations involved got so cumbersome that he had to invent a special convention to keep those things in check. Now, we are not going to do things which are as complicated as in general relativity. Our scope of discussion is much simpler. But even there, using Einstein's summation convention will actually help us cut down the clutter in a lot of our work. So first, let's take a look at the convention. But before we can do that, we need to do some relabeling. When we talk of vectors, we talk in terms of their x, y and z components and the basis vectors I, j, k, at least when we are using the Cartesian coordinate system. For the rest of this lecture, at least most of the rest of this lecture, I'm going to assume that I'm working in the Cartesian coordinate system. What I must assure you is that the identities we derive will be valid in all coordinate systems, but they would usually be easier to work out in the Cartesian. Now, instead of using ax, ay, az for the three components of a vector A, I'm going to change notation a bit. I'm just going to write A1, A2 and A3. Similarly, instead of the three basis vectors I, j and k, I'm going to introduce a notation E hat 1, E hat 2, E hat 3. The hat, of course, signifying that these are unit vectors. 1, 2, 3 stands in for x, y and z respectively. Now the reason why we do that is the following. First of all, a general vector with components ax, ay, az, of course, can be written down as axi plus ayj plus azk, which a new convention becomes a1, e1 plus a2, e2 plus a3, e3. And you can now see the advantage. I can use a summation notation and write this in a more compact fashion. I can just say this is ai, ei, with I summed over from 1 to 3. Now the summation of an index which is repeated, in this case I, which comes twice in this expression, is so very common that Einstein introduced a convention for this. The convention was simply this, that if an index is repeated in an expression, unless otherwise stated, we are going to sum up over all possible values of that index. So instead of writing sum over I going from 1 to 3 AI, EI, the convention simply says that I'm going to write AI, EI, and that's it. The moment I write AI, EI, the convention tells us that this means A1, E1 plus A2, E2 plus A3, E3. This might look like a very small thing to do at this stage, just dropping a sigma sign, but in calculations which involves lots of summations or products of sums and so on, this convention actually makes life a lot easier. One very important thing has to be borne in mind. This index that you have, which is being summed over, is actually a dummy index. In other words, it doesn't really have a specific value. You cannot say I equals 1 or 2 or 3 here. You have to put in all values of I and then add up. So instead of writing this as AI E hat I, you could have written this as AJ E hat J or AK E hat K or any index which you want. Just repeat it twice. So dummy indices can be relabeled. That's a very important thing to bear in mind. Now at this stage, let me just point out one thing. When Einstein introduced his convention in general relativity, he had two different kinds of objects, so-called contravariant and covariant vectors to worry about. So he had two different types of indices written upstairs or downstairs. And there the convention essentially was, if a pair of indices is repeated, one upstairs, that is as a superfix, and one downstairs as a suffix, something which looks like this, AIBI, then it's going to be summed over. Indices which are both in the lower position would not really be. But that was for a more complicated setting. We don't really want to worry about that right now. For us, all indices will be downstairs and the rule will be, if two indices are repeated, they are going to be summed over. Now this summation convention will be used not only for components and basis vectors, like in the case here. If you have something like AIBI, where AIs and BIs are numbers, AIBI will be read as A1B1 plus A2B2 plus A3B3. Similarly, CIDI will be C1D1 plus C2D2 plus C3D3. Now here I have to sound a very important warning, which is this. We will often have occasion to multiply two such sums. Say AIBI, which of course means sum over I going from 1 to 3 of this, and CIDI, another similar sum. Now when you multiply these two things, the result will not be AIBI CIDI, which would simply mean A1B1 C1D1 plus A2B2 C2D2 plus A3B3 C3D3. As you can very easily see, multiplying this with this will give, in addition to these three terms, also other terms like A1B1 C2D2 or A1B1 C3D3 and so on. Writing AIBI CIDI for the product would give you a mistake simply because all these cross terms will not be taken into account. And this is where we have to be careful. What we must ensure is that when I'm multiplying these kind of stuff, I do not inadvertently use repeating indices. Note that in this expression, I is a dummy index, so is this. So I could have written J here or J here or K here or whatever. What is important is when I'm multiplying them together, the fact that these indices could very well have been different becomes important. When I remove the bracket here and multiply everything together, I will have to write AIBI CJDJ, which means this is an expression where you're going to multiply all these four pieces and add up with I and J both running over 1 to 3. And you should be able to convince yourself very easily that doing this will actually give you the desired product of this and this. So inadvertently repeating indices can be a problem if you're dealing with a large calculation. You have to be wary of that. And that essentially is the one important thing that can trip you up when you're doing calculations involving the summation convention. If you are careful about this, almost certainly you will find most of these calculations pretty easy to do. Now that we have understood the convention, let us try to use this and see what this has to say about simple operations in vector algebra. Let's start with really simple operations, some of the most basic ones in vector algebra, like multiplication of a vector A by a scalar alpha. Note that in our convention, the vector A is written as AIEI, and there is a summation over I which is just implied. What this translates to is simply alpha AIEI. This, of course, is a very, very familiar result. It just tells us that when you multiply a vector by a scalar, all three of the components get multiplied by the same scalar. But what you can see here is that all you have done is just remove the bracket in between alpha and AIEI, and you have got your result. Frankly, this hides a very important property of vector algebra, which is things like this. The fact that scalar multiplication distributes over vector addition. If you think of AIEI summed over I as a sum of three vectors, A1, E1, A2, E2 and A3, E3, what this removal of the bracket has done is essentially implemented this. The other major operation that you have to do with vectors, at least in vector algebra, the major preliminary operation is adding two vectors. And here again, the vector A can be written down as AIEI. Vector B could be written down as, let me be just a bit capricious here and write that as BJEJ. In simplifying this expression, what has to be remembered is dummy indices can be changed at will, except when you have inadvertent repeated indices in a product. Here, these two things are separate and they are not being multiplied. So it would actually be much better for you to start out with this. In other words, if you did not have BIEI to begin with, if for some capricious reason you wrote this as BJEJ, you would have to change it to BIEI first and then rewrite this simply as AI plus BI times EI, which is of course a very, very familiar result that when you add two vectors, their components add. So these were the really trivial applications of the basic idea. Now let us go on to something a bit more non-trivial, although pretty simple, which is the dot product. And in talking about the dot product, we will meet our first major new introduction in this lecture, which is the Kronecker delta symbol. But first, let's take a look at the dot product. Well, A dot B is simply AIEI, where I have put in a bracket here to show you that this is a sum which you have to do separately, dot with BIEI, and the bracket here is essential. The brackets tell you that this sum and this sum have to be done separately, independent of each other, which is why if you want to remove the bracket, what you have to do is change the dummy index here. That is, change this to AIEI.BJEJ. This is very, very important. The next step is simply rewriting this as simply AIBJ EI.EJ. This seems like a very simple result. After all you're doing is taking a dot product of one vector, which is a scalar times a vector, with another scalar times a vector, and you've just collected the scalars together. But remember, this is really not just the product of two vectors, this is a product of two sums. So what this apparently obvious thing does is that it hides behind it the fact that the dot product is distributive. So some very important properties of dot product, the fact that it distributes over addition, is actually being automatically implemented in this notation. The advantage of this summation convention is many of these things which would have needed at least a few sigma symbols and some thought becomes automatic in this. Now let us try to see what this means by writing it out. Once you get enough practice in this, you will not need to write this out explicitly, of course. That would essentially defeat the whole purpose. But because we are still new into this game, I would write down the term explicitly. Here, what this means is you have to let I run over all values from 1 to 3, and independent of it, j run over all values from 1 to 3. And in order to do this, you could of course write down the terms in any order you want, because these are finite sums. Rearranging the terms will not change the sum, but it always is useful to have a definite order in mind. Let's change j first for a fixed value of I, and then change I. That is, do this as a nested sum, with j being summed over first and then I being summed over. So I takes the values 1, 2 and 3, but for each I first add up over all values of j. So for I equals 1, I get the terms a1, e1, that's for the I, and then because j runs over 1 to 3, I get b1, e1, b2, e2 and b3, e3. With a1, e1 sitting in all three terms. That is, I is fixed at 1 for this row. The next row contains the terms for I equals 2, and then you have I equals 3 terms. So a total of 9 terms that are there in this dot product. And you can easily see that the important thing that you will need to proceed further is knowledge about what these dot products, the elementary dot products between basis vectors actually are. All these 9. And they are really very simple. From the basic definition of a dot product, that the dot product of two vectors is a scalar which is equal to the product of the magnitudes times the cosine of the angle between them, it follows that for these three mutually perpendicular unit vectors, ei dot ej will be 1 only if you are dotting the vector with itself, that is, only if I equals j, otherwise it will be 0. Now this kind of a symbol with two indices, depending on I and j as in this case, which vanishes whenever the two indices are different and is 1 when the two indices are equal, is so useful that it has got its own special symbol and its own name. It's called delta ij. That's a symbol, and it's called the Kronecker delta symbol. Once again, delta ij simply means it's something which depends on I and j. It's 1 when I and j are equal and 0 whenever they are unequal. So, going back to our compact notation, a dot b, which is ai bj ei dot ej, remember? But we have just written down ei dot ej as delta ij. So I get ai bj delta ij. Now one very important thing here is that here both I and j are being summed over. And whenever a Kronecker delta symbol takes part in a sum, things become very easy. Now here you are summing up over both I and j. So you must take a decision. Which one will you sum up first? Will you sum up over I first or j first? Let's say I sum up over j first. Now when I sum up over j, the presence of a Kronecker delta symbol in the sum involving j as an index does the following. It simply picks out those terms in the sum where the two indices are equal, that is, where j is the same as I. Remember, I is fixed when you are summing up over j. There, this delta ij will simply pick up those terms where j is equal to I and drop the rest, because you will get 0 for delta ij for the rest. So, since you are summing up of ai bj delta ij, ai of course is not being summed up at this stage, it will be summed up later. The bj delta ij simply becomes bi into 1, of course. So, ai bi is what you end up with. Okay, to put this in a nutshell, whenever you have a delta ij and that's summed over, you just replace the summation index by the other index in the whole expression. Here you are summing up over j first, so you just replace in the rest of the expression all j's by the other index, that is I, and you get ai bi, which of course means a1 b1 plus a2 b2 plus a3 b3. What would have happened if you had decided to sum over I first? Well, once again simple. If you are adding up over I, what you have to do, because of the delta ij, is you have to replace all i's in the expression by the other index, that is j. If you did that, you will get with aj, bj. The delta ij will go away. In the rest of the expression, you will have this substitution of indices. Now, aj, bj may look different from ai, bi, but as we have already said several times, this I or j are both dummy indices. It doesn't matter what you call them. aj, bj is also the same as a1, b1 plus a2, b2 plus a3, b3. So, the choice of adding up over j first simply changes the final expression's appearance, but not what the final expression really is. The final expression is always going to be a1, b1 plus a2, b2 plus a3, b3. Now, this is a formula for the dot product which should be very, very familiar to all of you. If you are taking the dot product of two vectors for which you know the Cartesian components, you just multiply the components together and then add them up. And that's what this formula is telling you. All we have done is use the delta ij symbol to shorten the calculation in between. And what is very important for us is that this has given us a new symbol which will turn out to be very, very useful in what's going to come. Now, just to see some applications of this, let's take a look at this formula, ai, bi, that I have derived for the dot product in this convention. The application should be pretty familiar to you, but the derivation using this convention is a bit shorter, and that will be a portent of many more complicated results to come in the future. I'm talking about the derivative of a dot b. In this convention, it simply becomes ddt of ai bi. And although this is a sum, I'm going to just pretend that this is one term, basically because differentiating a sum is like differentiating each term and then adding up the results. So here, this simply becomes ai dbi dt plus dai dt bi. Here we are really using linearity of the derivative without really saying so. Once again, the fact that this convention allows you to make use of certain results without even thinking about them becomes very important. And ai dbi dt is nothing but the dot product of a vector with components a1, a2, a3, another one with components db1 dt, db2 dt, db3 dt. That's really a dot db dt. And similarly, this term is da dt dot b. So this result that you can differentiate a dot product of two vectors in the same way as any product, the proof of that is as short as this if you use the summation convention. And one immediate consequence of that is this very useful result, that if a vector A has a fixed length, then da dt is either 0, that is the vector itself doesn't change, or it's perpendicular to A. And the proof of that follows trivially from this. What we have written down is a derivative of a dot b. So let's talk about the derivative of a dot a, which is of course the length of A, and the derivative of that has to vanish if the length of A is fixed. So a dot A's ddt, which is 0, has to be the same as a dot da dt plus da dt dot A. That's twice a dot da dt. And if this is 0, this means a dot da dt is 0, and hence a and da dt are perpendicular to each other. Unless, of course, da dt vanishes. Let us next move on to the other major product of vectors, the cross product. This will give us an introduction to our second important symbol here, the so-called Levi-Civita symbol, or often called the epsilon symbol in short. To see what that is, let's start with A cross B. That's AI, EI cross BI, EI. And once again, before you remove the brackets, you have to be careful to change the dummy index. So this really is AI, EI cross BJ, EJ. And using the fact that cross product distributes over summations, and without even having to mention that, the summation convention allows you to write that as AI, BJ, EI cross EJ. Now what exactly is this vector EI cross EJ? It's a cross product of two basis vectors, and it is a vector. And like all vectors, it can be expanded in terms of E1, E2, E3. So if you write that as Ek times something, summed over k of course, the expansion coefficients that you will have, those somethings, will of course depend on the two vectors which are being taken the cross product of, that is I and j. It will also depend on which component you are talking about, that is on k. So the expansion coefficients will depend on I, j and k, and you can write Ei cross Ej as epsilon ijk Ek, summed over k of course. So the rule for figuring out these epsilon ijk symbols, the so-called Levi-Civita symbols, is simple. You take the ith basis vector and the jth basis vector, cross them together, and write down the result as an expansion in E1, E2, E3. The coefficient of Ek will be epsilon ijk. And following this prescription, we can easily figure out some of the values, in fact all of the values. For example, if you did I cross I, you would of course get 0. That's the standard result from cross products. That is E1 cross E1 is 0. So epsilon 1 1 k Ek is 0. So epsilon 1 1 k is 0 for all k. That is epsilon 1 1 1, 1 1 2 and 1 1 3 are all 0. On the other hand, I cross j equals k gives you in this language, new language, E1 cross E2 equals E3. So epsilon 1 to k Ek is E3 times 1. That means epsilon 1 to 1, epsilon 1 to 2 are 0, and epsilon 1 to 3 is plus 1. I am stressing on the plus in the plus 1 because if you were to do this in the other order, j cross I, that will give you minus k. That is E2 cross E1 is minus E3. And that tells you epsilon 2 1 1, epsilon 2 1 2 are 0, and epsilon 2 1 3 is minus 1. Now in this manner, I can go through the entire set, but it should be pretty easy to see that epsilon ijk can have a non-zero value only if all the three indices are different. After all, if I and j were equal, you were really taking the cross product of the same vector with itself. That would definitely give you 0. So epsilon ijk would definitely vanish if I and j were equal. But we also know that Ei cross Ej is perpendicular to both Ei and Ej. That means it does not have any projection in the direction of I and j. Therefore, when you take Ei cross Ej for different I and j, you are only going to get the third Ek with either a plus sign or a minus sign. So all the three have to be different. So they have to be 1, 2 and 3 in some order. And it's very easy to figure out from these basic rules for cross product that epsilon 1, 2, 3, epsilon 2, 3, 1, epsilon 3, 1, 2 are each plus 1. Epsilon 1, 2, 3 is plus 1 is something we have just seen from I cross j equals k. From j cross k equals I, you get epsilon 2, 3, 1 equals 1. And k cross I equals j gives you epsilon 3, 1, 2 equals plus 1. There are three other cases where all three indices can be different. And these are epsilon 2, 1, 3, 1, 3, 2, 3, 2, 1. And from the anti-commutativity of the cross product, it follows easily that all of these three have to be minus 1. So there are 27 possible values for epsilon I, j, k. Note that I, j and k can each take 3 values each. So 3 times 3 times 3, 27 values. But out of which only 6 are non-zero, 3 of which are plus 1, 3 of which are minus 1. Now a very compact way of stating this is that this Levi-Civita symbol epsilon ijk is the completely anti-symmetric symbol with 3 indices, with epsilon 1 to 3 being given by plus 1. Now the complete anti-symmetry guarantees that whenever 2 of the indices are equal, the result will be 0, simply because complete anti-symmetry means whenever you switch 2 indices, the thing changes sign. And if these 2 indices happen to be equal, then interchanging them should not change the thing, but it should also change the sign. And the only thing which changes sign without changing itself is 0. So, this complete anti-symmetry guarantees that you will get a non-zero value only if all the indices are different. And if you know epsilon 1, 2, 3, from that, using interchanges, you can get all the other possibilities. For example, if you want to go from epsilon 1, 2, 3 to epsilon 2, 1, 3, you are really interchanging two indices of 1, 2, 3, and complete anti-symmetry means that gives you minus 1. On the other hand, epsilon 2, 3, 1, if you want to get there from 1, 2, 3, you can interchange these two, but that will give you 2, 1, 3. Then you have to interchange 1, 3 again to get 2, 3, 1. And that gives you a pair of minus signs. And of course, multiplying two minus signs gives you a plus. That's why epsilon 2, 3, 1 is plus. Now with 3 indices, which is what you need in 3 dimensions, things are pretty easy to state in terms of cyclic and anti-cyclic permutations. Remember 1, 2, 3 is what you call a cyclic permutation. 1, 2, 3, 2, 3, 1, 3, 1, any one of these. Cyclically permuting 1, 2, 3 gives rise to all 3 of these. And they all give a plus 1. To get to 2, 1, 3, you have to permute these anti-cyclically. And that gives you minus 1. So another short way of saying this is epsilon ijk has to be all different. If the ijk's are a cyclic permutation of 1, 2, 3, you get plus 1. If it's an anti-cyclic permutation, you get a minus 1. Note that this works only in 3 dimensions, because in 3 dimensions, all possible permutations can be broken up into cyclic or anti-cyclic permutations. In 4 dimensions, for example, you would have 4 indices, 1, 2, 3, 4, and the change 1, 3, 2, 4 is neither cyclic nor anti-cyclic. Of course, you can get to here by one interchange, and therefore if you had a 4-dimensional epsilon symbol, and you do, there epsilon 1, 2, 3, 4 would be defined as 1, and epsilon 1, 3, 2, 4 will be minus 1 because of one interchange. The rule of complete anti-symmetry still works no matter which dimension you are in, but this cyclic permutation rule for finding out all possible values of epsilon ijk works only in 3 dimensions. Now that's the only thing that we have to worry about in the rest of this lecture, because we are stuck with a 3-dimensional world in these lectures. Using this epsilon symbol, we can write down the cross product of 2 vectors in a very compact fashion. Note that we have already gone a long way towards it when I wrote A cross B as AI Bj Ei cross Ej. But now we know that Ei cross Ej is expanded in terms of the basis vectors in the form epsilon ijk ek. So, the upshot of all this is A cross B is epsilon ijk ai bj ek. Or the kth component of A cross B. This is going to be very useful in later applications, is given by epsilon ijk ai bj. By the way, you can write this in the form epsilon kij ai bj, expressing simply because epsilon ijk and epsilon kij being cyclic permutations are exactly the same. Now using this compact notation, let me prove a result which should be very trivial, but the proof actually gives you the inkling of a technique that we will use several times later. A cross A, we all know it should be 0, but let's try proving that using this notation. Of course, A cross A will simply become epsilon ijk ai aj ek. Now here, what is important is that I, j and k are all dummy indices of summation. So I can change them to be anything I want. In particular, I can interchange their names. I can call I, j, and instead of what I was calling j, I can call that I. So doing that, in a consistent fashion throughout will give me epsilon j I k aj ai ek. But epsilon j I k is what you can get from epsilon I j k, the original version, by doing a single interchange of I and j. And therefore, epsilon j I k is minus epsilon I j k. On the other hand, aj ai and ai aj are one and the same. These are just numbers, so they commute with each other. And therefore, you end up with a cross a being negative of this expression, which is a cross a again. So a cross a is minus a cross a, and therefore it has to be 0. Note that this is a special example of something that we will use very often. If you had an anti-symmetric symbol, say aij, which changes sign when I and j are interchanged, and a symmetric quantity sij, which stays the same when I and j are interchanged. And if you had formed this sum of products, aij, sij of course has 9 terms, where I runs from 1 to 3 and j runs from 1 to 3, and they're all added up together. Here again, because of the fact that I can interchange the two indices without changing the thing, I can write this. But since aji is negative of aij, and sji is the same as sij, that is the stated symmetry and anti-symmetry properties, you get aij, sij is negative of itself, so has to be 0. So this kind of an entity, which is called a contraction between an antisymmetric and a symmetric object, will always lead to 0. A special case of that was seen here. Epsilon ijk is antisymmetric in I and j. Ai aj is symmetric in I and j. And their contraction, sum where I and j are both summed over, will be 0. Okay, this was rather trivial. At least the result was rather trivial. Let us try to take a look at something a bit less trivial, which is the scalar triple product. A combination of 3 vectors which yields a scalar A dot B cross C. Here I have not put in a bracket, but here the lack of the bracket is not because I can do this in any order. I haven't put in a bracket because there's only one order in which this expression makes sense. You have to do B cross C first and then do A dot with that. Now A dotted with B cross C is simply AI times B cross C's ith component. And B cross C's ith component will simply be epsilon jki bjck. Here I have put the component index at the end. I could have also written this as epsilon ijk bjck. Equally well. And in fact, that is what I have done in the very next step. I have written this as epsilon ijk ai bjck. Note once again that this is really a sum over j and k, and here you are multiplying this with ai and adding up. All of that has been subsumed in this simplified notation where the summations are all implied. So once again, we have just used the fact that a product with ai distributes over the sum here when I wrote this down. Now, in order to see what this means, let us once again write this out in full. Once again, we are doing this only because we are new to the game. Once we get used to this, we will not have to actually write down an expansion to see what this means. It should be obvious from the form itself. But at least let me point out one thing. Here you have a sum over I, j and k. 3 indices, each of which take 3 values. So this sum should have 27 terms, out of which only 6 will be non-zero because of the epsilon ijk's total antisymmetry. And let us just write down those 6 terms, where ijk happen to be a cyclic permutation of 1, 2, 3. That is 1, 2, 3, 2, 3, 1 and 3, 1, 2. You are going to get plus sign. In the other 3 terms, you are going to get a minus sign. That's why this sum only reduces to this 6 terms: A1, B2, C3, A2, B3, C1, A3, B1, C2. Here I, j and k have been permuted cyclically and hence leads to a plus sign. In the other three terms, you have an anticyclic permutation and you get a minus sign. Now by combining the terms with A1 together, I get A1 into B2C3 minus B3C2, which is nothing but the determinant formed by putting B2B3 in one row and C2C3 in another. A2, if I take that common for the other two terms with minus sign, I get the determinant B1, B3, C1, C3. And A3 is multiplied by the determinant with elements B1, B2, C1, C2. And it's very easy to see that all of this really boils down to a single 3 by 3 determinant, where the three rows are the three components each of the three vectors. A1, A2, A3, B1, B2, B3, C1, C2, C3. Now this determinant form for the scalar triple product should be pretty familiar to most of you who have done a course in vector algebra. But the compact version, epsilon ijk ai bj ck, means exactly that, and it is going to be very useful in figuring out properties of this quantity. As an example of how useful this notation that we have introduced is, let's take another look at this expression. And let's try to figure out the relationship between this quantity and this B dot C cross A, where you have the same three vectors but permuted in a cyclic fashion. So this, of course, will be Bi Cj Ak. Now, one thing we can always do is use the fact that these components commute to write this in this fashion. Ak Bi Cj. All I have done is move the Ak to the beginning of this expression. But now note that the indices on the ABC components were I, J, K in the original version of A dot B cross C. Here it is Kij, but Kij and Ijk are actually cyclical permutes of each other. In fact, if I replace K by I by J, J by K, I end up with Ijk. Now let's try to do that here. I will just replace all the K's by I. That is just a special case of relabeling. Instead of interchanging two labels which we had done before, we are cyclically permuting the labels. So wherever you had K, you will replace that by I. Wherever you have I, you will replace that by J. And wherever you have J, you will replace that by K. You have to do it consistently, of course, on both the vector components and the epsilon. So let's try that. Epsilon I, the I gets replaced by J. What about J here? J gets replaced by K. And K at the end gets replaced by I. On the other hand, doing that on the components simply gives you AI, BJ, CK. Now, epsilon JKI and epsilon IJK are exactly the same because these indices are cyclically permuted versions of these indices. So this is epsilon IJK, AI, BJ, CK, which means that B dot C cross A is exactly the same as A dot B cross C. You may actually know another way of proving this identity already, and that would involve the fact that if you looked at the determinant version of the expression, A dot B cross C is a determinant of a matrix where A, B, and C make up the three rows. B dot C cross A would have B1, B2, B3, C1, C2, C3, and A1, A2, A3 as the three rows. And you have to calculate the determinant for this. Elementary determinant theory that in order to go from here to here, I would have to make this row jump across two rows, and that will give you two interchanges, hence two minus signs, and therefore an overall plus sign. So using the determinant also, you could have easily shown that these two things are equal. But I would suggest that once you get some practice into this relabeling indices and stuff like that, this version of the formula may actually be easier to use. Let us now take a look at a very important identity involving the product of two epsilon symbols. Although I say product, I really mean that it looks like a product, it's actually a sum of a product. It will not be an exaggeration to say that this identity is perhaps the single most important identity that you will come to use in this context. But to set the context for this identity, let me just take a look at something which is very familiar to all of you. A product involving three vectors which yields a vector as a result, the so-called vector triple product A cross B cross C. And by writing out A, B and C in terms of their components, it can be easily seen that this is the same as AI, BJ, CK, EI cross EJ cross EK. Let us now forget about the vector triple product in general for the time being and take a look at this particular combination, this particular specific vector triple product, that of three basis vectors. Now, EI cross EJ cross EK can be simplified using what we have learned, simply using the fact that EJ cross EK by definition is given by epsilon JKL EL, where L is some dummy index. Note that as far as this index is concerned, I could have taken it to be anything other than the ones which are already in use. I, J and K here are not dummy indices. You can say things like, let's talk about I equal to 3 and see what the result is going to be. You can give specific values to I, J or K here. Free indices must match on two sides of an expression. Dummy indices, on the other hand, have no specific significance other than specifying a sum, and you can replace a dummy index by anything other than other dummy indices in the product or by free indices. I could call this epsilon JKL EL or epsilon JKM EM or epsilon JKN EN, but I could not have called this epsilon JKI EI, because then this I and this I would have been confused. Having said that, the next step is trivial. I pull the epsilon JKL out of this and I write the result as epsilon JKL EI cross EL. This again is the cross product of two basis vectors, and from the definition of the epsilon symbol, it's easy to see that I can write that again in this form. Epsilon IL, a dummy index, in this case I've used M, EM. So I have epsilon JKL, epsilon IL, M, EM, where this is really a product of two epsilon symbols, but it's more than that. As I've said, it's not just a product, it's a product on which a summation over L has been implied. Now in this form, the L is in two different places, at the end here and in the middle here, and in this form it's a bit difficult to keep track of things. So what I will do is I will move the L in this epsilon symbol to the back by cyclically permuting all the indices. So this becomes epsilon MIL. So the important thing is I am going to investigate the contraction, sum of products of epsilon JKL and epsilon MIL, and the dummy index which is being summed over is in the same position in both. In this case, it's at the end in both, but you should also realize that I could have also written this as LJK epsilon LMI with equal ease, where both the indices would be sitting at the front. That's also perfectly legitimate, and that would be equal to this expression. Once again, cyclically permuting JKL to get to LJK makes no change whatsoever. Similarly, MIL has been cyclically permuted to LMI. So what we are going to do is we are going to take a look at a contraction like this, a sum of a product where in this case I have taken I as a dummy index, the first index on both of the epsilons, and the other four indices J, K, L, M are free. Of course, this result should depend on J, K, L and M only, cannot depend on the value of I, because I after all is summed over all the possible values. And of course, if I write it down in full, it will look like epsilon 1 JK, epsilon 1 LM, epsilon 2 JK, epsilon 2 LM, epsilon 3 JK, epsilon 3 LM. Now let me remind you of one thing. The epsilon ijk is completely anti-symmetric, and as a result, it will vanish unless all of the three indices are different. That means that first of all, j and k cannot be equal to each other, l and m cannot be equal to each other, in which case all three terms would vanish. But even if j and k were different and l and m were different, it would also still be rather difficult for this sum not to be zero. The only way in which you can get any one term here not to be zero is the following. I've already said that j cannot be equal to k and l cannot be equal to m. But in addition, you must realize that if, for example, this term is to be non-zero, jk has to be 2, 3 or 3, 2. But then, epsilon 1 lm, which is multiplied by it, also must be non-zero, and therefore the only way you can get a non-zero product here is jk has to be 2, 3 or 3, 2. Lm also has to be the same set 2, 3 or 3, 2. Of course, that would give this term, the first term, a non-zero value. Could have got a non-zero value from any of the other two terms as well, but in each case it's easy to see that whatever pair of values j and k have, l and m must have the same value as a set. That is, jk must be as a set the same as lm. And in each case, it's obvious that only one of the three terms in this sum is going to end up giving you a non-zero result. So if j is the same as l and k is the same as m, then only one of these terms will give you a non-zero result, and in that term, both the epsilons will be identical. They will be either both plus 1 or both minus 1. So the product in that case will be plus 1. So this sum of products, which ultimately is just the one product term which survives, will be plus 1. If on the other hand j is equal to m and k is equal to l, you must have minus 1. Putting all this together, we can write down our identity. Epsilon ijk, epsilon ilm, where I is the dummy index which is being summed over, will either give you delta jl times delta km, a plus 1 from that, or give you a minus 1 from delta jm delta kl. Note that if both of these terms are non-zero at the same time, that is, both of these terms give you 1, that can only happen if j and k are equal or l and m are equal, in which case, of course, you should get 0 from the first demand that we made, and that's exactly what you get. The two ones in that case would cancel each other out. So what we end up with is this identity which allows us to replace the contraction of two epsilons with some delta symbols. And delta symbols are always nice to work with in a sum. Going back to our original or almost original thing that we looked at, the vector triple product of three basis vectors ei cross ej cross ek, which remember was epsilon jkl, epsilon mil em. Here, it's of course the same as the L sitting at the front in both cases. Now, in order to use this formula, what is important to remember is the following. Your dummy index has to be in the same position on both epsilons, either both at the beginning or both at the end. Indeed, both at the middle would also work. But once you do that, if you look at the rest of the indices, you have a structure like this, where your deltas taken between indices taken from one epsilon and the other. If you take the first index from both epsilons, first index other than the dummy index, that is, here j and l, and of course that means the second indices also go together. So first indices go together, second indices go together, that comes with a plus sign. First index here goes with the second index here, second index here goes with the first index here. That term comes with a minus sign. This is simply what we had learned here and here. So putting that to use here, I don't have to memorize the formula. It's just the first, second, minus first, second, first that I remember. So here this is going to be delta of Jm. Here remember is a dummy index. Delta Ki, first, second, minus delta Ji delta Km times Em. Now when you multiply this out, remember that this is not just a multiplication. A sum over m is still implied here. Delta Jm Em summed over m means you are going to end up with Ej. So you get delta Ik Ej minus delta Ji or delta Ij, they are both of course the same. And delta Km Em becomes Ek hat here. So that's my Ei cross Ej cross Ek. And using that I can get back my expression for the vector triple product. Rather familiar expression which I'm pretty sure you have all proven in many different ways before. But what you get here is one of the quickest ways of proving this. This is Ai Bj Ck Ei cross Ej cross Ek. That's something we had already worked out before. It took me only one step to go from A cross B cross C to this. Then I replace the Ei cross Ej cross Ek by this expression. And now once again you have a sum over K here, also a sum over I. But let's say I do the sum over K first, which means all the K's in this expression gets replaced by I. So I get Ai, Bj, Ci, Ej. Here, all the J's get replaced by I. So I get Ai, Bi, Ck, Ek or Cj, Ej. Okay, I've actually done one more step here. It should have come out to be Ck, Ek directly, but there I've just replaced the K dummy index by J here. So now let's take a look at the things together. Bj, Ej go together. That's nothing but the vector B. Ai, Ci on the other hand is A dot C. So this is B vector into A dot C. This on the other hand is A dot B, Ai, Bi, and Cj, Ej or Ck, Ek, whatever you call it, is C vector. So you get the famous back minus cab rule for the vector triple product. A cross B cross C is B vector into A dot C minus C vector into A dot B. Well, this could be called our very first application of the very important contraction that we learned about. But you will see that this particular identity comes back over and over again in many, many different applications. This brings our foray into vector algebra to an end for today. As we promised, in the next lecture we are going to come back with the tools that we have picked up today, like the summation convention, the delta symbol and the epsilon symbol, and use them to study vector calculus. Just as an appetizer, you can see on your screens right now the forms that our nabla operator, the gradient of a scalar, divergence of a vector, and the curl of a vector field will take in this new notation. In the next lecture, we will see why the forms are like this, and then we will be able to use these forms and the identities that we have picked up today to prove a lot of vector identities in a very, very simple manner. Bye till the next lecture.